This is the fourth and final video in a series which aims to make sense of organic mechanisms. And this video looks at choosing the type of mechanism. Sometimes you're shown some reactants and you're asked to state the type of mechanism that will be involved, draw the curly arrows. And so this video will give explanation of the strategies to use here and some examples for you to work on. Just to set the scene, here's an example. You could be shown this pair of species and asked to state the mechanism type and draw the curly arrows. It's not that you're supposed to know the name of every single mechanism in organic chemistry. There's a huge range and only a certain number of them are relevant at A level. But for the ones that you are expected to know, you can be asked this kind of question. Obviously, one strategy would be to simply try and memorize all possibilities just by sight, but it's always easier and more secure to memorize things if you understand some principles of what's going on. So this video will equip you with some tools to be able to look at this, and even if you have half an inkling just from straight memory by looking at it, you'll be able to check that with some good principles. In case you're wondering, in this case it would be a nucleophilic addition mechanism, but we'll explore more of that in a moment. The names of mechanisms are always made up of two words, and so in order to be able to choose the mechanism, it really helps if you understand what those words mean and then can relate them to what you're seeing in terms of the reactants. The first word in the name relates to the type of attack, and there's really three words here: electrophilic, nucleophilic, and radical. So at A level, the mechanisms you're supposed to be able to recall always start with one of those three words. And the second word in the name relates to the type of reaction that then happens. And addition and substitution are the two that you'll need to know at A level. So various combinations of these: electrophilic addition, electrophilic substitution, nucleophilic addition, nucleophilic substitution, and radical substitution are the ones that you're expected to know at A level. Just to be complete here, let's stress the fact that there's actually other types of organic reactions that you should be able to talk about at A level, shown there in yellow, but they're not ones that you need to know mechanisms for. So we'll unpack these words and we'll start with the attack words and nucleophilic first of all. What does nucleophilic mean? Well, simply it means that the reaction involves attack by a nucleophile, which doesn't tell us very much. So what is a nucleophile? And rather a long definition here, and one that you are supposed to be able to recall from memory. So worth spending a bit of time on. So what is a nucleophile? It's a species, and in chemistry, by species we mean an ion or a molecule. It's a sort of a general word, a catch-all word. So a species with a negative charge, that could be a full ionic negative charge or just a partial negative charge delta minus, and a lone pair of electrons. It's going to be attracted to a positively charged carbon. Now that again could be a carbon with a full ionic positive charge, but mostly a partial positive charge delta plus. And the nucleophile will donate a pair of electrons to that positively charged carbon, forming a covalent bond to it. To help make that a bit clearer, let's look at an example. Here is a classic nucleophile. Think about the definition: a species with a negative charge. Well, our chloride ion here has a full ionic negative charge, and a lone pair of electrons. Well, chloride ion actually has 4 lone pairs of electrons, so great nucleophile. It's attracted to a positively charged carbon. So here's a molecule that it could attack. It's got a delta plus carbon because of the bond to the oxygen, which is more electronegative than the carbon. And the definition then carried on to say that the nucleophile would donate a pair of electrons to that positively charged carbon, forming a covalent bond to it. So the nucleophilic attack at the beginning looks like this. The second attack possibility was electrophilic, so let's unpack that now. What is electrophilic? Well, it means a reaction that involves attack by an electrophile. Again, that doesn't tell us very much, so what's an electrophile? Another long definition for you. An electrophile is a species, this time with a positive charge. Now again, that could be an ionic positive charge or a delta plus, a partial positive charge, and it's going to be attracted to a region of high electron density. Bit of a strange phrase, just really meaning a region where there is a particularly large amount of electrons gathered, something like a double bond. And this time the electrophile, instead of donating a pair of electrons to, can accept a pair of electrons from that region of high electron density, forming a covalent bond to it. So let's look at an example of that. Here's an electrophile. It's got a positive charge on it, this time a delta plus, a partial positive on the hydrogen due to that polar bond to the chlorine. So this can act as an electrophile. What's an electrophile attracted to? Well, a region of high electron density. There's the double bond between the two carbons in this molecule, a sigma bond and a pi bond, 4 electrons in total, which will attract that delta plus H. And the definition carries on that the electrophile with its positive charge will accept a pair of electrons from the region of high electron density, forming a covalent bond to it. So that's a classic beginning of an electrophilic attack there. The third and final type of attack that you need to know is a radical attack. So what do we mean by radical attack? Well, it involves attack by a radical. What is a radical? This was discussed in some length in the third video in the Making Sense of Organic Mechanisms series, so I'm not going to dwell on it in detail here. The point though really with radicals is that they attack just about anything. So whereas the nucleophile and the electrophile attacked organic molecules with particular features, a positively charged carbon or a region of high electron density, radicals kind of represent our last resort. They don't need a functional group of some kind to interact with in the organic molecule. They'll simply attack anything. They're not the first choice, however, because it's very unpredictable what they'll actually do. It's very hard to control, and you tend to get a mixture of products. Let's just illustrate this though. Here's a classic radical, the chlorine atom, 7 electrons in its outer shell, so 1 unpaired electron, and a radical attack involves that, snatching an atom normally off another molecule by using its unpaired electron to form a bond together with 1 electron from an existing bond in the molecule that it's attacking. So here's a challenge for you to check your growing understanding. 5 organic molecules. Take a look at them, see if you can decide from what we've said what kind of attack they would be vulnerable to. So looking at number 1, it's only open to radical attack. It doesn't have any functional groups, no positively charged carbon, no region of high electron density, so it's only really a radical that could get that to react. Number 2, however, has a polar bond, a CO bond, and so we have a partially positive carbon, and that's going to make it open to nucleophilic attack. Number 3, we've got the region of high electron density, that carbon-carbon double bond, and that's going to make it vulnerable to attack by electrophiles. Number 4, we've got a polar bond again with a delta plus carbon, partially positive carbon, that make it open to nucleophilic attack. And number 5, with those 6 delocalized pi electrons in the ring, as well as the sigma bonding, we've got a region of high electron density there, and so that's open to electrophilic attack. Of course, you will get molecules with more than one functional group in, sometimes meaning that they could be attacked by electrophiles and nucleophiles, in which case, if you're having to decide what's going to happen, you need to look at what's attacking and see whether it fits the requirements of a nucleophile with a negative charge and a lone pair of electrons, or an electrophile with a positive charge that could therefore accept a pair of electrons. We'll turn our attention now to the word that's the second part of the mechanism name that relates to the type of reaction, and consider first of all addition reaction. So what's meant by an addition reaction? The definition you need to know: 2 or more molecules join to make a larger molecule, and essentially the clue in a molecule that this is what will happen is that there'll be a double or a triple bond present. That we don't come across triple bonds very much, and that allows new extra bonds to be made to the molecule, allowing other things to add on. To illustrate that, let's look at a couple of examples. So the organic molecule here has carbon-carbon double bond, which allows an addition reaction to take place. So the water molecule can add on to the molecule in the form of an H at one end of the double bond and an OH at the other, which actually gives 2 possible products depending on which end the 2 bits attach. Second example, this time not with a carbon-carbon double bond, in the organic molecule, but a carbon-oxygen double bond, again allows addition. That double bond can turn to a single bond, allowing the HCN to be added to the molecule with an H at one end of the double bond and the CN at the other end of the double bond. The second possibility you need to know for the type of reaction, the second part of the name of a mechanism, is substitution. So what do we mean by a substitution reaction? Well, the definition is one group of atoms in a molecule is replaced by another group of atoms. When does this happen? Well, in a way it's our only option if we don't have a double or triple bond present in the molecule. If we're going to attach anything else to the molecule, something's going to have to leave. So substitution is when one thing in the organic molecule is swapped for something else. And some examples just to illustrate that: the reaction of chlorine and methane. If we're going to put a chlorine atom onto the carbon, we're going to have to lose something. Carbon can only form 4 bonds, so we'll replace one of the hydrogens with a chlorine. So the hydrogen has been substituted with a chlorine atom there. Second example, with 2-chlorobutane here reacting with a hydroxide ion. For the hydroxide ion to attach to our chain, something's got to leave. There aren't any double or triple bonds to play around with, so substitution is our only option, and we can substitute the chlorine for the hydroxide, producing butan 2-ol and a chloride ion. The final example is perhaps the one that is most open to question. The benzene ring does have something almost approaching the idea of sort of double bonds. However, the pi electrons here are delocalized around the ring in a very stable way, which is not easily disrupted. So our only option here is substitution. In order to put a bromine onto the ring, we'll need to take a hydrogen off. And so we get a substitution of a bromine for a hydrogen on the benzene ring, producing the bromobenzene and hydrogen bromide. What follows now will be a series of challenges for you to test out your understanding, get some feedback. Don't be afraid to go back and listen to the ideas again if things aren't working for you initially. So to start with, here's a pair of reactants, and your challenge: what type of mechanism would be involved here? The answer should be nucleophilic substitution. If we look at the molecule, it is open to nucleophilic attack. It's got a partially positive carbon where you've got the carbon attached to the oxygen, and the attacking chloride ion fits the bill for a nucleophile. It's got a negative charge and a lone pair of electrons. In terms of the type of reaction, without any double or triple bonds present, if we're going to stick that chloride ion, the chlorine, on somewhere, then something is going to have to be lost. So definitely a substitution reaction. So next question, what would be the products then? Have a think, see what you can suggest. And the substitution would be the OH coming off as a hydroxide ion to make the chloroethane. For these named mechanisms, you do need to be able to do the curly arrows. So the final challenge for this bit is to suggest a curly arrow mechanism. Maybe you've got some memorized ideas about it, but see if you can use what we've just been saying about what nucleophilic attack is and what substitution means to think logically about what the arrows should be. Pause the video, have a go. We'll go through the answers in a moment. So here we have the reactants drawn out a little bit more full structurally. It's always important to put the partial charges on, and that reveals our delta plus carbon. So nucleophilic attack is the lone pair on the nucleophile donating a pair of electrons to the positively charged carbon to form a covalent bond. Substitution means something's got to leave. And we met earlier in the series the idea that bonds tend to break with electrons going onto a more electronegative atom. So that CO bond is a perfect opportunity for the electronegative oxygen, more electronegative than the carbon, to grab the electrons that it's attracting towards itself anyway. That's going to give us the new bond between the C and the Cl for the chloroethane, and separate off the OH with now a negative charge on the oxygen where the arrow went towards it, making a hydroxide ion. Here's your next challenge then, and again, first question is to choose the type of mechanism. Pause the video, make your mind up. And you should have said electrophilic substitution. If we look at the benzene ring, opportunity for electrophilic attack, region of high electron density, and the NO2 plus fits the bill for an electrophile, positively charged species that could accept a pair of electrons. Substitution is our only option here. The benzene ring with the delocalized electrons is very stable, doesn't tend to do addition reactions, so it's going to be substitution. Next question, predicting the products. And you should have shown the NO2 substituting for an H, with the H coming off as an H+. One little tip for you is that overall charge is always maintained. So if you look at the reactants, we've got a neutral molecule, the benzene, and a positive ion, the NO2. So overall, if we add all that up, it's a 1+ charge. Our products, therefore, are also going to have overall a 1+ charge. Charge is conserved in a reaction. Your final challenge for this bit to suggest a mechanism. It is one of the mechanisms you need to know. So C, combination of recall and also thinking about the strategies we've been talking about, if you can suggest how this might happen. And the correct mechanism is as follows. The donation of a pair of electrons from the region of high electron density to the positively charged electrophile to form a covalent bond. That gives us initially this unstable carbocation type intermediate with the positive charge, which we show as kind of delocalized in the ring as opposed to any specific point. The hydrogen I've drawn there was already there, just not drawn in the skeletal diagram, but we've put it on at this point to allow the next step to be drawn, which is then the H leaving and those electrons going back into the ring to restore the delocalized 6 pi electron system that the benzene ring has. And the H comes off as an H+, with the arrow heading away from it, making it positive. Next challenge, pause the video, choose the type of mechanism. And you should have said nucleophilic addition. In terms of the type of attack, this is an interesting one because, of course, we've got a delta plus carbon with the CO bond being polar. We also have a region of high electron density with the carbon to oxygen double bond there. So it's fair to say that in the cases you'll see, if there is a delta plus carbon and you have something with a negative charge, which we've got the cyanide ion, Cn-, then it's more likely to be a nucleophilic attack than an electrophilic attack. So go with the nucleophilic option if nucleophilic is possible. In terms of the type of reaction, we can do addition here. We've got a double bond that can turn to a single bond, so allowing extra things to be added. So second question, what are the products? And with addition, we can have the H and the Cn from the HCN being added at either end of the double bond. Note, of course, that it's the Cn that attaches to what was the delta plus carbon, because that's where the nucleophilic attack would take place. So the H is going to attach to the O, not the other way around. And final challenge, final bit for this challenge, suggest the curly arrow mechanism for this nucleophilic addition reaction. So we're going to start with a nucleophilic attack, which means that the lone pair of electrons on our negatively charged nucleophile will be donated to the positively charged carbon. We've got the delta plus carbon in that polar bond there to form a covalent bond. And then with addition, we've got to have that double bond turning to a single bond. So we can have that one of those double bond breaking, the pi bond breaking with the electrons, as usual, going on to the more electronegative atom, the oxygen. And that's going to give us an intermediate like this, with the bond now formed between the carbon of the cyanide ion and what was the delta plus carbon, and a negative charge on the oxygen at the end of what is now a single bond. The second step then, the H plus from the hydrogen cyanide can then be make a bond to the oxygen using the lone pair of electrons on the oxygen, giving us our final product. It is possible that you did the whole thing in one go, with the double bond breaking to form a bond between the oxygen and the H plus ion, rather than this two-step process here. And there is some flexibility allowed generally with these questions, but it's best to represent it as more than one step when you've got several things going on. So here's your final challenge. As before, first bit, choose the type of mechanism. And you should have chosen radical substitution. With our ethane as the organic molecule there aren't any functional groups, nothing to allow nucleophilic or electrophilic attack, which means that we have to go to our last resort, radical reaction. And in terms of the type of reaction, it's a saturated molecule, the ethane, so if we're going to put anything on there, then we're going to have to take something off, so substitution required. What then would be the products of this reaction? And this is rather open to question because radical reactions are so unpredictable and uncontrollable, but an initial most likely product would be the substitution of just one hydrogen for a bromine. Further substitution can and probably will occur depending on how long the reaction is allowed to run for. And this is a reaction that you should be able to suggest the curly arrow mechanism for. So thinking about radical attack, radical type reactions, what do you think a mechanism could be? Pause the video, sketch something out, and check your answer in a moment. So this is going to involve multiple steps. First step is initiation, and it's the halogen that breaks in initiation, something to get used to there. So we've got this initiation step, the homolytic fission of the Br-Br bond to make bromine radicals. Bromine radical can then attack something, and the only thing of relevance for it to attack here is the ethane molecule. And we can do a classic propagation step where the bromine radical grabs a hydrogen off the ethane molecule with a CH bond breaking homolytically, giving us HBr as an initial product and now an ethyl radical. That ethyl radical, now very reactive, can react with all kinds of things, but in terms of having moving towards products, the relevant reaction here is a second propagation step involving the ethyl radical reacting with a Br2 molecule. Again, classic sort of propagation thing where it grabs a bromine atom from the Br2 molecule and produces another bromine radical as a result. Of course, radical reactions also involve termination steps, so we could carry on and suggest all sorts of other steps. You could have two ethyl radicals joining to make butane. You could have had the ethyl radical reacting with a bromine radical to make bromoethane in a termination style step instead of a propagation style step as shown. So there's lots of flexibility for what happens next in these radical reactions. But the two propagation steps as shown there represent a kind of repeating cycle which will churn out the main products of this reaction. So the bromine radical regenerated in the second step, propagation step, can then attack another ethane in the first propagation step, making an ethyl radical which attacks a Br2, and so on and so on and so on. So those really are the key, most likely steps, and you should represent those when asked to come up with the radical substitution mechanism for a halogen and an alkane.